Alright, in this video we're going to look at the definition of the triple integral for a function of x, y, and z. So we're going to be in rectangular coordinates if we've got a function of x, y, and z. So we've gone through this so far for a double integral in rectangular coordinates and a double integral in polar coordinates. And so at this point you should understand the basic structure. And then really what we want to just think about here is what would be the slightly different details for this definition as opposed to double integrals. Alright, so for all of these definitions that we're looking at here, we need to have our function be defined. So it has to have outputs on the region we're integrating over. And we want that region to be closed and bounded. So for all of these definitions, we basically start that same way. We establish that we have a function whose domain includes the region that we're integrating over, and we need to make sure that the region we're integrating over is closed and bounded. So that's the same from single integrals in Calc 1, double integrals that we did in rectangular coordinates, and double integrals in polar coordinates. The really big difference here between what we did before is that our region is in R3 instead of just in R2. Alright, and then the same when we did the Legos, the basic idea was that we chopped that region up. And so that's a partition. Since we're in rectangular coordinates, we're going to use a rectangular partition. So if we think about our region D is some three-dimensional region, closed and bounded, whatever that might look like. And then we're going to partition that using an inner rectangular partition. We need to have an inner partition because our function may not be defined outside of our region, so we need to make sure that the pieces of what we chop up are actually in the domain of the function. And a rectangular partition, so that would mean that the sides of our pieces of our partition are parallel to the coordinate axes. So I drew an XYZ coordinate system here. So basically that means that our pieces in the partition here are going to be little boxes. So I'm not going to draw a whole bunch of them because that would be kind of hard to draw here. But the idea is that I'm going to chop this region up into little boxes with sides parallel to the X, Y, and Z axes. So it's the same as the idea we did in double integrals. We had our region in R2 and we chopped that up into little rectangles. Alright, and then we want to choose a point in each of those boxes in the partition. So within each of these boxes we're going to choose a little point somewhere in there. And then the idea of choosing those points is that we use those to get function outputs. Okay, so my function of three variables here, I don't have enough axes to draw that. So if I have three input variables, I'd need a fourth axis for the output variables. So I don't have enough axes to draw that, but we can think about that we just get a number as an output for the function there. And then the basic idea is that I want to take function outputs times the size of the pieces in our partition. So we need some notation for size of the pieces. The objects in our partition are little three-dimensional boxes, so the size of those boxes would be volumes. So since we have a rectangular partition here, our volume of those boxes, we would have a delta y, the way I have this one drawn here, k, and a delta xk, and a delta zk as the three dimensions of the box. So we could rewrite that delta v sub k as delta x sub k, delta y sub k, delta z sub k. Alright, and then we basically want to form our Riemann sum. That's our Riemann sum. And then we want to take the limit as the size of the partition approaches 0, and also then that would force us to have infinitely many boxes in our partition. So we need to establish what our norm of the partition is, and just like before, we're going to let that be the length of the longest diagonal. Okay, and so when we let the limit as the norm of that partition approaches 0, provided this limit is the same for all choices of partition, there were two places where we made choices of partition and choices of points, then we define that to be our triple integral. Alright, so that defines our triple integral in rectangular coordinates. In the next video, we'll look at some extensions of Fubini's theorem to triple integrals and an example of evaluating a triple integral.